Thank you for joining us for the last of our ray diagrams for mirrors. This is for concave mirror case 3, where the distance to the object will be greater than the center of curvature. I had to sharpen my pencil, that's why it's already partially drawn here. We're going to put the center point about right here. We're going to put this guy out as far as we can and still hit a line. I'll bet you that's 19 boxes away, because that's what's happened the last couple of times now. And we're going to draw these in place. Okay. There's our center of curvature. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, of course. 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half is my focal point. There we go. This is a very far away image, such as the mirror, where it's reduced, so I don't have to draw it very small. I can draw it a little bit larger. This time it is way out here, so let's draw it 6 boxes high this time. Okay, so there's our arrow that we're going to try to draw a rendition of. I don't really need a ruler to draw a parallel line on top of graph paper, but whatever. Strikes there. There's my P ray. Parallel one outgoing from my object. It is going to bounce back so that it goes through the focal point. Let's see if I can be as accurate with this diagram as I was with the last one, where I shocked myself by having the calculated location be exactly where the diagram location was. Okay, next we're going to use that central point 1, and let's see, that was 6 up, so 6 down, 2, 4, 6. So I'm going to aim at this spot right here. Okay, so my mid line, like I said before, if I was only going to draw 2 lines, I think it would be these two. My parallel one that goes through my focal point, which is the way we expect that we would like concave mirrors to react like, even if they are from parabolic reflectors. Alright, now I am very strongly going to go with that. As a matter of fact, I am going to use this as an example and say that's all I'm going to draw. And so we're going to say that our image is right here. Now we're going to verify that with calculations, so don't just take my word for it that that kind of looks right. I do know that it does kind of look right. It is supposed to be smaller and inverted like the camera looked. So let's measure a few things. We put our object, let's see, that was at 19, so 20, 21, 22, 23, 24, 25. So the distance to our object was 25. Our focal length distance was 9.5 again. What else do we need? The height of our object was 6. Okay, so we're going to first calculate our distance. Now we've done the same calculation several times over, and we always end up rewriting it to this, so I'm going to jump to it. 1 over the distance to my image is equal to 1 over the focal length minus 1 over the distance to my object. So that's 1 over positive 9.5 minus 1 over 25. And I'm going to grab my calculator real quick, which I've covered under our last diagram. And I'm going to put in there 9.5. I'm going to invert that. I'm going to subtract from that 25 inverted, and I get 0.065. That's not the answer. I want the inverse of that. So I hit that again, and we get 15.3. 15.3 boxes away. Now, with 15.3 under our belt, we're going to figure out what our, actually, one thing I keep missing is I don't actually calculate the magnification. The magnification is the negative of the distance to our image over the distance to our object. The negative, the distance to my image is, we just calculated it at 15.3. Positive because it's in the real world. And then the distance to my object was 25. M is therefore equal to a negative 15.3 divided by 25, a negative 0.612. That's not my final answer, so I'm being a little heavy with the sig figs. If I wanted to know what height my object is going to be, since magnification is also equal to the height of the object over the height, oops, wrong way, height of the image, I'm going to blame it on the inverted image here, height of my image over the height of my object, then the height of my image is equal to the height of my object multiplied by my magnification factor. So that is, oh, and I forgot the minus outside there. So that's going to be equal to 6 multiplied by negative 0.612. So the height of my image should be a negative 3.7. Okay, let's check. My object is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, something or other. I was pretty dang close. I was 14.7, and that's 15.3. That's not too bad. And my image height should be negative 3.7. This is negative 1, 2, 3, 0.6. All right, so that was a little bit closer. But once again, you get a general approximation, and you can usually survive with 2 rays. If I drew some further rays, we might find that they're more in this vicinity here, which is where the true answer looks like it should have been about right here, which is almost exactly where we're at. Okay, now let's look at what happens when we are in case 3 and we are beyond this. Now, hopefully you've noticed some symmetry. Before, in case 2, we were between the focal point and the center point. And we had an object that became enlarged and inverted. And of course, this is the inverse of that one because it's right side up and this one's upside down. So this is just playing that one backwards. Now, in both cases, our object was out here and our final result was somewhere along this ray here, somewhere along our parallel ray. And if we're in this case where we're out beyond the center point, it seems to be between the center point and the focal point. When we were closer here, then it seemed to come out beyond the center point. Okay, I'm just going to let you know right now that if we put it at the center point, it will show up at the center point. Maybe we want to do a calculation with that in one last treatment as we look at the special locations, the focal point and the center of curvature for locations. Now, anyway, so if our object is out there, what we end up with is something which is inverted. And what told me that it was inverted was that my magnification was negative, which of course came from the fact that my height was negative if I just measured it off of here. So either my magnification is negative or the image height is negative. Either one gives me the fact that it's an inverted image. It is real. It's out here in front of the mirror, which means, of course, that the distance to my image is positive. It is located between, the distance to my image is located in between the focal point and the center of curvature. And as far as magnification goes, it is reduced because the absolute value of my magnification was less than 1. We found our magnification to be 0.612. It was negative. That's why we always want that absolute value bar there. Thank you for looking at this last treatment of ray diagrams with mirrors. Actually, I should rephrase that. I think we may come back and look at what happens at the focal point, what happens at the center of curvature.